Welcome to the TOEFL listening section. In this part, you will hear one or more conversations in an academic or campus context, such as a discussion between a student and a professor or between two students. You may take notes while listening. Listen to part of a conversation. You will hear it only once, so listen carefully. After the conversation, you will answer questions about what you heard. Some questions will ask you about main ideas and details. Others will ask about implied meaning, speaker attitude, or how ideas relate to one another. Use both what is stated and what is implied to answer.
Good morning, Professor Ramirez. Thanks for meeting with me during office hours.
Good morning, Mark. No problem. You said you wanted to discuss your thesis on plate tectonics and earthquake prediction.
Yes, I am trying to refine my research question about how seismic monitoring techniques can improve short-term forecasts on active fault lines.
That is a very current problem. When you say short-term forecast, do you mean hours to days or weeks to months?
Primarily hours to days. I want to evaluate early warning potential from foreshock sequences and slow slip events.
Good. Distinguish between prediction and early warning. Prediction implies saying exactly when and where before the main shock. Early warning detects a rupture in progress and alerts people seconds or minutes before strong shaking arrives.
Right. Historically, exact prediction has been elusive. But can dense instrumentation change that, or at least improve probabilistic forecasts?
Dense instrumentation helps. High-density seismic networks, continuous GPS arrays, and interferometric synthetic aperture radar, or InSAR, give different kinds of data about strain and slip-on faults.
Could you explain how GPS helps, since seismometers record shaking and microseismicity?
Continuous GPS measures ground deformation with millimeter precision. Over months and years, it shows how plates are accumulating strain on a locked patch. Short-term changes can indicate transient deformation like slow slip.
So combining GPS and seismic data can reveal both the locked state and transient events that might precede a rupture.
Exactly. For example, the Cascadia subduction zone exhibits episodic tremor and slip. Those slow slip events change stress on neighboring locked segments and may influence timing of large earthquakes.
You mentioned tremor. How does low-frequency tremor differ from regular microseismicity in terms of prediction value?
Low-frequency tremor is a sustained, low-amplitude signal often associated with slow slip. Microseismicity are discrete, small earthquakes. Tremor indicates aseismic slip, which can transfer stress but may not be a clear precursor by itself.
Is the Parkfield experiment an example of where prediction failed despite dense monitoring?
Yes. Parkfield was forecast to experience a moderate earthquake based on a historical quasi-periodicity. The expected event did not occur on schedule, which showed limits of recurrence interval-based predictions and the complexity of fault behavior.
So we need to rely on real-time signals rather than assuming strict periodic cycles.
Correct. Real-time monitoring can capture foreshock patterns, changes in seismic velocity, and slow slip. Also, changes in background seismic noise can be informative.
Can seismic tomography or velocity changes actually indicate increased stress before a quake?
Yes. Temporal seismic tomography or ambient noise interferometry can detect changes in seismic wave speeds in the crust. A decrease in velocity may indicate increased cracking or fluid movement, which sometimes precedes larger events.
You mentioned fluids. How important are fluids in the fault zone for triggering earthquakes?
Fluids reduce effective normal stress and can lubricate faults. Pore pressure changes from fluids migrating into a fault can destabilize it and trigger seismicity, including slow slip.
What about machine learning approaches that analyze continuous seismic data for precursory patterns?
Machine learning has promise. It can detect subtle patterns in large datasets, like continuous waveform streams. For instance, algorithms have identified foreshock clusters and tremor signatures that human analysts missed.
Are there successful case studies where combining ML and dense monitoring provided actionable warnings?
One example is improved real-time detection of microseismic swarms in Japan that helped refine probabilistic hazard during aftershock sequences. But operational predictive success is still limited and requires careful validation to avoid false alarms.
How do we evaluate predictive skill without causing false alarms that erode public trust?
We use probabilistic seismic hazard analysis and forecast verification metrics. Communicating uncertainty clearly is essential. Early warning systems that announce strong shaking in seconds are more mature and have defined performance standards.
Could you give an example of how Coulomb stress transfer plays into prediction models?
Coulomb stress calculations estimate how slip on one fault segment increases or decreases stress on adjacent segments. After a large event, Coulomb models help forecast where aftershocks or triggered events are more likely to occur.
So after the 2011 Tohoku earthquake, Coulomb stress mapping showed increased risk on nearby faults?
Yes. Tohoku redistributed stress across the subduction interface and outer rise, and those calculations helped explain subsequent seismicity patterns.
For my thesis, I want to focus on a case study. Would the San Andreas transform or the Cascadia subduction be better?
Both are excellent. San Andreas has abundant seismic and geodetic data and well-studied locked patches. Cascadia offers episodic tremor and slow slip that ties plate tectonics to transient signals. Choose based on whether you want to emphasize transform fault dynamics or subduction processes.
I am leaning toward Cascadia because I want to study slow slip and its interaction with locked megathrust patches.
Then you should incorporate continuous GPS, tremor catalogs, and regional seismic networks. Also consider paleoseismic records to constrain recurrence intervals for the megathrust.
How can paleoseismic data be combined with modern monitoring for better probabilistic forecasts?
Paleoseismology gives long-term recurrence statistics and size of past earthquakes. Modern monitoring shows short-term state of stress and transient events. Together they constrain both the long-term probability and the immediate likelihood given current deformation.
One more question about instrumentation. Should I recommend adding borehole seismometers to reduce noise?
Yes. Borehole broadband seismometers reduce cultural noise and improve detection of small events and tremor. That increases the signal-to-noise ratio for automated detection and machine learning models.
Great. For my methodology, I will compare continuous seismic detections, GPS-derived slip transients, and Coulomb stress change models for a Cascadia segment.
That sounds solid. Make sure to include verification metrics and a plan for false alarm assessment. Also discuss how early warning systems differ from predictive systems.
Will do. Thank you for the guidance and the case study suggestions.
You are welcome. Keep me updated on your data sources and your initial results next month.
Listen again to part of the conversation. Then answer the question.
For our model, the most useful signal is the pattern of persistent microseismicity and slow slip that changes stress on nearby locked patches.
This concludes the conversation portion. For more TOEFL practice tests and study materials, visit Spinta.org.